Problem number 2 reads, two charges, one of -5 microcoulombs and the other of +3 microcoulombs, are placed 40 centimeters apart along the x-axis. Where must a third charge be placed along the x-axis if the net force on it is to be 0? Let's take a look at our charges. Here we see the two charges separated by a distance of 40 centimeters. Before you try to work this problem, let's see if we can determine where this third charge is to be placed. Let's assume that our third charge is positive. We have three choices as to where it could be placed. It could be placed in this region here to the right of our positive charge. It could be placed between the two charges. It could be placed to the left of the negative charge. Let's assume that we place it between our two charges and see whether or not the net force on it could be 0. For the net force on this charge to be 0, the magnitude of the two forces would have to be the same, and the two forces would have to be in opposite directions so that they could cancel one another out. Let's look at the forces on this positive test charge due to our two charges. The force due to the 3 microcoulomb charge is repulsive and would be to the left. The force due to the -5 microcoulomb charge is attractive and would also be to the left. These two forces could be equal in magnitude, but they cannot be opposite in directions, therefore they can never cancel one another out. Our charge cannot be between the positive and negative charge. Let's look at the situation to the left of our negative charge. Over here, if we look at the forces acting upon our test charge, we would have the -5 microcoulomb charge will exert a force on it to the right. The +3 microcoulomb charge would exert a force on it to the left. Now the directions here are all right. These two forces are in opposite directions, but they can never be equal in magnitude. The force due to the closer -5 microcoulomb charge will always be larger in magnitude than the force due to the further away 3 microcoulomb charge. This region is out. The only thing left to try is to the right of our plus charge, so let's look at the situation over here. The force due to our +3 microcoulomb charge would be to the right. The force due to the -5 microcoulomb charge would be to the left. They are in opposite directions, so it's possible that they could cancel if they're equal in magnitude, and it is possible for them to be equal in magnitude because our positive test charge is closer to the smaller in magnitude 3 microcoulomb charge, and it's possible for the force due to that 3 microcoulomb charge to be equal in magnitude to the force due to the further away, but larger in magnitude, -5 microcoulomb charge. So this is the region in which we should place our charge. Let's do one other thing. Let's call the distance between the +3 microcoulomb charge and our test charge the distance x. Stop your VCR at this point and try to solve that problem. Here is a figure where I have changed the 40 centimeters to 0.4 meters. I've labeled our third charge, charge Q. The force due to the 3 microcoulomb charge, I've labeled F sub 3, and that due to the 5 microcoulomb charge, F sub 5. The condition that the net force on charge Q be equal to 0 implies that the magnitude F5 is equal to the magnitude of F3. Writing F5 using Coulomb's law, we would have the Coulomb constant K times 5 microcoulombs multiplied by the charge Q divided by the distance between their centers, which is x plus 0.4 meters, and that quantity is to be squared. Notice that I did not put in a -5 microcoulombs here. The magnitude of this force is what we are interested in. The directions have already been taken care of by means of our diagram. This is to be equal to F3, which is K, times 3 microcoulombs multiplied by the charge Q divided by x squared. The problem is to find x, and we have to solve this equation for x. Let's first of all cancel out some common terms. There's a k on both sides that can be canceled. There's a q on both sides that can be canceled. That indicates that the charge q, both its magnitude and its sign, is irrelevant to the problem. We've been calling q a plus charge. We could have just as easily called it a negative charge, and our arguments would be exactly the same. Can also cancel the units, microcoulombs on both sides, and then rewrite with what is left cross multiplying. We would have on the left 5x squared, and on the right we would have 3 multiplied by x plus 0.4 meters, and I'm going to drop the unit meter for the time being. It tends to be confusing if left in here, and that is to be squared. All right. Let us square the quantity in parentheses. This then is 5x squared is equal to 3 times x squared plus 2 times x times 0.4 plus 0.4 squared, which is 0.16. And if we multiply the right-hand side through by 3, we have 3x squared plus 2.4 times x plus 0.48. And if I collect my terms on the left, then I would have 2x squared. And moving the 2.4x over to the left, minus 2.4x, and then minus 0.48. That this is all equal to 0. That we recognize as a quadratic equation, and it is in the typical form of a quadratic equation. If we examine that, it is the constant ax squared plus a constant b times x plus a constant c is equal to 0, and the standard solution to that is that x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. Let's apply this equation to our problem. Solving for x here, we would have that x then is equal to minus b, and that's equal then to minus a minus 2.4 is our value of b, plus or minus the square root of b squared. That's minus 2.4, the quantity squared, minus 4 times a, which is 2, times c, which is minus 0.48. This is all to be divided by 2a, which is 2 multiplied by 2. If you work this out in the calculator, you should confirm that this comes out to be 2.4 plus or minus 3.10 divided by 2 times 2 is 4, and that this results in 2 answers. Using the plus sign, this comes out to be 1.37 meters. We'll put my units back in here, and using the negative sign, this comes out to be minus 0.175 meters. Which one to use? Well, let's go back to our figure to see if we can tell. The 1.37 meters corresponds to the charge Q placed over in the position shown in the figure. The minus value indicates that the charge Q would be placed in here. Now, we have already examined that situation, and we have determined that it is possible for the magnitudes of the forces to be the same in this region. However, it is not possible for them to cancel out because they are in the same direction. So we reject the negative solution and we take the positive solution that x is equal to 1.37 meters, and that is the solution to our problem. Let us move on then to problem number 3.